Download this code from codegive.com, link in the description below. Analog to digital conversion, ADC, time, a deep dive. Analog to digital converters, ADCs, are essential components in interfacing the analog world with digital systems. They convert continuous analog signals, like voltage or current, into discrete digital representations that microcontrollers, microprocessors, and computers can process. Understanding the timing characteristics of an ADC is crucial for ensuring accurate and reliable data acquisition. This tutorial will provide a comprehensive overview of ADC conversion time, its impact on your application, and strategies for optimizing it. 1. Why ADC conversion time matters ****. Sampling rate and Nyquist theorem ***. The conversion time directly affects the maximum achievable sampling rate. According to the Nyquist-Shannon sampling theorem, the sampling rate must be at least twice the highest frequency component present in the analog signal to avoid aliasing, distortion. If the ADC takes too long to convert, you might not be able to accurately capture fast-changing signals. Real-time performance in real-time applications, example control systems, data logging, the ADC must convert signals quickly enough to react to changes in the environment in a timely manner. A slow ADC could lead to delays and instability in the system. Power consumption while not the primary factor, longer conversion times can indirectly contribute to higher power consumption, especially if the ADC needs to be actively powered during the entire conversion process. Multiplexed inputs if you're using a single ADC to sample multiple analog inputs, through a multiplexer, the conversion time determines how quickly you can cycle through all the inputs and acquire data. 2. Factors affecting ADC conversion time ***. The total conversion time for an ADC is influenced by several factors, which vary depending on the ADC architecture, manufacturer specifications, and configuration settings. Architecture Different ADC architectures have inherent speed limitations. Flash ADC the fastest type, performing conversion in a single step. However, flash ADCs require a large number of comparators, making them expensive and power-hungry, especially for high resolutions. Successive approximation register, SAR, ADC a widely used architecture that balances speed, cost, and power consumption. It iteratively compares the input voltage to a series of known voltages, converging to the digital representation. Sigma delta, delta sigma, ADC excellent for high-resolution, low-frequency applications. They use oversampling and noise shaping to achieve high accuracy but typically have slower conversion rates than SAR ADCs. Integrating ADC, dual-slope ADC another type suitable for high-resolution, low-frequency applications, offering good noise immunity. Commonly used in digital voltmeters. Resolution the resolution of the ADC, number of bits, has a significant impact on conversion time, particularly for SAR ADCs. Higher resolution requires more comparison steps, leading to a longer conversion. For example, a 12-bit SAR ADC generally takes longer to convert than an 8-bit SAR ADC. Clock frequency The ADC typically relies on a clock signal to drive the conversion process. A higher clock frequency generally results in faster conversion times. However, the clock frequency is often limited by the ADC specifications and the settling time of internal circuitry, comparators, DACs. Acquisition time, sampling time before conversion can begin. The ADC's input sampling capacitor needs to charge to the input voltage. This charging process requires a finite amount of time, known as the acquisition time. The source impedance of the analog signal and the input capacitance of the ADC influence the required acquisition time. A higher source impedance necessitates a longer acquisition time. Conversion cycles. Many ADCs require a specific number of clock cycles to complete a conversion. This number is usually specified in the datasheet. Oversampling and averaging. Some applications use oversampling, sampling at a rate significantly higher than the Nyquist rate, and averaging multiple samples to improve the signal-to-noise ratio, SNR. While this enhances accuracy, it increases the effective conversion time. Software overhead. The time spent on software operations related to the ADC, such as configuring the ADC, initiating conversion, reading the digital result, and processing the data, can also contribute to the overall time taken to acquire and use the analog data. 3. Calculating ADC conversion time. The conversion time is often provided in the ADC's datasheet. However, you might need to calculate it based on the specified parameters. Here's a breakdown of how to estimate the conversion time, particularly for SAR ADCs, the most common type. Acquisition time, T_. Data sheets often provide a minimum required acquisition time. If not, it can be estimated using the RC time constant, T_5 *R_source *C_sample. R_source, the output impedance of the analog signal source. C_sample, the ADC's input sampling capacitance, found in the datasheet. Conversion cycles, N_cycles, the number of clock cycles required for a single conversion. This is typically specified in the datasheet. For SAR ADCs, it's often related to the ADC resolution. Clock period, T_CLK, the inverse of the ADC clock frequency, T_CLK equals 1/f_CLK. Example calculation. Let's say we have an ADC with the following specifications. Architecture, SAR. Resolution, 12 bits. Clock frequency, f_CLK 1 MHz, clock period T_CLK equals 1s. Acquisition time, T_2s. Conversion cycles, N_cycles 12. Total conversion time equals 2s plus 12 1s equals 14s. Maximum sampling rate The maximum sampling rate, f_s, is the inverse of the total conversion time. f_s equals 1/total conversion time equals 1/14s 71.4 kHz. 4. Code examples and optimization strategies. Let's illustrate how to configure and use an ADC, along with optimization techniques, using Arduino, 8mg328P, as an example. The principles apply to other microcontrollers as well. 4.1. Basic ADC usage, Arduino. This is the simplest way to read an analog value using the analog read function. However, it doesn't provide much control over the ADC's configuration and conversion time. 4.2. Optimizing ADC conversion time, Arduino/8mg328P. The 8mg328P's ADC has several configurable parameters that can be adjusted to optimize conversion time and accuracy. Prescaler *. The ADC clock is derived from the system clock using a prescaler. A lower prescaler value results in a higher ADC clock frequency and faster conversion. However, The ADC clock frequency must be within the recommended range, 50 kHz to 200 kHz for optimal accuracy on the ATmega 328P. Asterisk reference voltage asterisk the reference voltage determines the range of the analog input. Using the internal 1.1V reference voltage can provide higher resolution for low voltage signals. Asterisk free running mode asterisk configure the ADC to operate in free running mode, where it continuously converts the analog input without requiring explicit triggering for each conversion. This can significantly reduce software overhead. Asterisk interrupts asterisk use ADC interrupts to handle the completion of the conversion in the background. This allows the main program loop to continue executing while the ADC is converting. Explanation of the optimized code asterisk. 1 Volatile int sensor value. The sensor value variable is declared as volatile because it's accessed both within the main loop and within the ADC interrupt service routine, ISR. This prevents the compiler from optimizing access to this variable in ways that might lead to incorrect values. 2 ISR, ADC_vect, this is the ADC interrupt service routine. It's automatically executed whenever the ADC completes a conversion. Inside the ISR, sensor value equals ADC, the ADC result, stored in the ADC register, which is a 16-bit representation of ADCL and ADCH, is read and stored in the sensor value variable. 3 ADXRA equals 180. This line enables the ADC, ADN, and enables the ADC interrupt, 80. When the ADC completes a conversion, it triggers the interrupt, which in turn executes the ISR, ADC_vect, function. 4 ADXRA equals 108, enables auto-triggering. The ADC starts a new conversion automatically after the previous one completes. 5 ADXRA equals 0, selects the auto-trigger source. Setting it to 0 enables free running mode. 6 ADXRA equals 1 ADSC, starts the first conversion. The ADC then continues converting automatically due to the auto-triggering feature. Key improvements asterisk. Asterisk faster conversion time asterisk by setting the prescaler to divide by 16, we've increased the ADC clock frequency, reducing the individual conversion time. Asterisk continuous sampling asterisk free running mode eliminates the need to manually start each conversion in the loop. Asterisk asynchronous operation asterisk the ADC conversions occur independently in the background, allowing the main loop to execute without being blocked by the ADC. This improves responsiveness. Asterisk lower overhead asterisk using interrupts reduces the overhead associated with checking for conversion completion. 4.3 Further considerations and advanced techniques asterisk asterisk. Asterisk differential ADC asterisk some ADCs support differential inputs, which measure the voltage difference between two input pins. This can improve noise immunity and reduce common mode noise. Asterisk external triggering asterisk instead of free running mode, you can use an external signal to trigger ADC conversions. This is useful for synchronizing data acquisition with other events in the system. Asterisk double buffering asterisk using double buffering, two memory locations for storing ADC results, can prevent data loss if the main loop is slower than the ADC conversion rate. Asterisk calibration asterisk calibrate the ADC to compensate for offset and gain errors. This can significantly improve accuracy, especially in demanding applications. 5. Troubleshooting ADC issues asterisk asterisk. Asterisk incorrect readings asterisk. Asterisk noise asterisk use filtering techniques, hardware or software, to reduce noise in the analog signal. Asterisk insufficient acquisition time asterisk increase the acquisition delay. Asterisk grounding issues. Asterisk ensure proper grounding to minimize noise and voltage offsets. Asterisk reference voltage instability. Asterisk check the stability of the ADC's reference voltage. Asterisk slow conversion rate. Asterisk prescaler setting. Asterisk verify that the ADC clock frequency is within the recommended range. Asterisk software overhead. Asterisk optimize the code to reduce the time spent on ADC related operations. Asterisk aliasing. Asterisk ensure that the sampling rate is at least twice the highest frequency component in the analog signal. 6. Conclusion. Asterisk. Understanding ADC conversion time and its influencing factors is vital for achieving accurate and efficient data acquisition in embedded systems. By carefully selecting the appropriate ADC architecture, configuring the ADC parameters, and employing optimization techniques, you can maximize the performance of your analog-to-digital conversion process. Always consult the ADC's datasheet for specific details and recommendations. Remember to balance speed, accuracy, and power consumption to meet the requirements of your application.